Много се радвам да говорим това събитие. Много благодаря за поканата. За съжаление нямам възможност да присъствам на място заради
To be
различни
part of
административни
the
причини.
event.
Малкият
Unfortunately, due
бонус,
to
който получавам за това, е, че сутринта
various
нямаше нужда да
mishaps,
чакам
I
телевизия
can't
пред мен, за да се записате.
be at the conference in
За
person.
съжаление, няма да можем да
Unfortunately,
поговорим за
we
програмиране.
won't be able
Наистина
to
съжалявам.
talk
Това за
about
програмиране, за
programming,
компютърни
and
новини и
I
социална
regret
сигурност.
this,
В
and
случай да се вържем, ще се радвам,
cybersecurity.
че
But if you would like to get in touch, we can
един
do
успешен
so
успех на бъдещото
on
събитие.
social
Тъй като
media
настоявате да
or
се събитието
meet at a
на
future
конференцията е на
event.
английски, ще председателствам на
And because
събитието.
the official language of the conference is
So
English, I will speak in
thank you very much
English
for
from
having
here
me. I'm
on.
really impressed by the quality of the conference that Acronis puts together. I'm really thankful that I'm a speaker on this event. And well, let's get started. I hope you all see my screen. So the topic of my presentation is not going to be only security related. Basically, we're going to have some security subtopics, but the main purpose of this presentation is to show you how at Google we're building JavaScript at large scale. Some of these practices are going to be applicable for small projects as well. So yeah, bear with me. I'm an engineer in the Angular team at Google, and let me start with the agenda for today. So basically, first, we're going to cover the evolution of the web. What actually requires us to introduce a build process in the development of modern web user interface. Right after that, we're going to take a look at Google 3, which is our monorepo, which helps us to manage our source code more efficiently and reuse infrastructure. As next step, we're going to take a look at how we're building JavaScript applications at Google. And finally, we're going to discuss some open source tools that can help us to achieve similar effects. So what is the web platform? Well, this is just a collection of technologies which are developed as open standards by W3C and some other standardization bodies. I think the key part here is that we have open standards. I think this is maybe the biggest distinguishment of a web platform compared to other alternatives, other platforms which did not make it over the years. We have different organizations with different interests, which are working together in order to power the business, leading edge technologies. So the web platform consists of different network protocols, such as HTTP, we have WebSockets, TOS, and others. We have programming languages, such as JavaScript. I put even CSS here because CSS together with HTML5, they're actually Turing complete. So every problem computable with a Turing machine is actually computable with CSS and HTML5 as well. Interesting fact. We have different browser APIs, such as web workers, web audio, we have local storage, service workers, and so many others. We have hundreds of APIs right now. But anyway, let us just take a look back in 1991. Back then, a lot of very exciting things for humanity happened in general. First, the Hubble telescope get launched to orbit around the Earth, and it took amazing photos of the entire universe, of places that, basically of the past of the universe, places that we have never expected to explore before. Back then, I wasn't very excited about anything. Basically, I was just a walking plant, so I was about to explore that year as well. Sir Berners-Lee, he released the first website ever, which was very simple. It was just HTML with different hyperlinks to other HTML documents. Back then, we didn't have any HTML. We didn't have any JavaScript and CSS, excuse me. No client-side scripting and styling at all. Everything we had was just very basic markup. We transferred over the wire using HTTP version 0.9, a protocol which specification you can read on one page. So life was much simpler. If we take 5 years forward in time, on 5th of March 1995, the development of a language which was about to change the industry started. We have JavaScript's age device. Pretty much any device has JavaScript virtual machine inside of it. So JavaScript is the most widely used language in general. It was about to change the web. We're going to start building very complex enterprise applications with it. So it was very essential for us as human species to do JavaScript right. About 9 days after that, JavaScript was born. This wasn't a huge space of planning, as you can imagine. JavaScript has a lot of issues right now that we're trying to fix with different languages which transfer out to JavaScript. JavaScript is basically our compilation target. And in the same time, we ask the business, what do you want? Do you want the power of desktop applications or the convenience of web apps? And of course, the business said that we want both, right? So we had to somehow make JavaScript work for large-scale applications as well. And this is what required us to complicate the entire development flow of web apps in 2019. Currently, in order to start a web application in 2019, we first need to pick a language which fits some of the problems that JavaScript has. For example, with Google, we're using TypeScript. It's a statically typed alternative of JavaScript. You can use either TypeScript like script or even CoffeeScript if you want to. We need to pick a minification tool in order to deliver very high quality, very small bundles to the browser. There are different tools for static code analysis, which can help us to discover some potentially security issues in our apps, or just make sure that we're following a style. There are different application frameworks, test runners, routing libraries, state management, and so many others. Everything is getting so complicated that we need another meta tool, such as scaffolding tool like Angular CLI or Create React App, in order to help us to bootstrap the entire build process. So this is getting even more complicated when we want to build applications in large organization, when the applications have to scale as well. In a company like Google, we face a lot of difficulty because of organization size as well. We have over about 100,000 employees, and huge chunk of them are actually engineers. So we have engineers with different backgrounds. We have projects with a variety of sizes. We have projects varying from a couple of thousands of lines of code to several millions of lines of code. And we need to somehow make our infrastructure, our infrastructure scale so that we can handle the project growth. We also need to provide very high quality development experience. For example, we would not want to have round-trip time between save of a JavaScript file reflecting the change in the browser in several seconds. We would want them to, we don't want to wait to make the developer wait several minutes actually. Maybe 1 second is fine, but more than because this is going to lead to a significant drop in productivity. Let's take a look at a very example. Let's take a look at Google Cloud. It's a very high level architecture of the entire project. Basically here, it looks like a traditional single page application where we have Google Cloud app. We have user interface, which depends on Angular material, and both depend on TypeScript. Angular material, of course, depends on Angular as well. On the other side, we have backend services, which just provide some APIs over different tools to the The only difference from a very traditional single-page application is that Google Cloud's UI is more than 10,000 files of TypeScript, or more than 2 million lines of code. That is a lot of code, as you can imagine. If we can try to build this application with the traditional state-of-the-art tooling in the web. For example, the first step would be to npm install in order to get Angular material, Angular, TypeScript, and a few other tools which are being used in the UI. But as you know, npm is kind of fake in general. First of all, if we run it as a super user, anyone can swipe out completely our file system just by adding rm-f/ and completely destroying our machine. But even if we ignore this, recently there was a very interesting security scandal that someone was stealing crypto coins by sneaking malicious source code in one popular npm package which had over 2 million downloads per week. And the owner of this package didn't have anything to say, and I can understand that. Although it was his fault in the end, just by inherently, NPM has a lot of security vulnerabilities itself. So in turn, we're not using NPM, but let's forget this. Let's try to build our application with Webpack. I don't know if you have ever tried to build an application with 2 million lines of code with Webpack, but that's pretty much what you get. You get out of memory, unfortunately. So we can work around this fact. What we can do is we can decompose Google Cloud Console into several sub-projects. We can have compute. The compute part can be one application. We can have the marketplace, which is second sub-project, and so on and so forth, basically. We can have separate Webpack configs for each individual sub-project. And in the end, we can just merge them together into one unified application. So this is something which is going to work. Basically, we're going to decompose the entire project into smaller sub-projects. Each of them can have several different build steps. You can combine them together in the end and get what you can see currently when you open cloud.google.com. We can even run individual steps in parallel, which is a great benefit. For example, here we're building in parallel the compute part, marketplace, and security part. So we can take advantage of the multi-processor nature of our machines. But here we suppose that the dependency graph of our project is very simple. We suppose that we have only one application which depends on small sub-projects. In reality, we can have cross sub-project dependencies. One sub-project may depend on the other, and we might not be able to build one project without building another one. So this means that our algorithm for building projects from the scale of Google Cloud should be a little bit different. We should first discover the build graph. So we should decompose the entire project into smaller sub-projects. We need to find out whether we have cycles in this graph, so we can run something like topological sort. We can distribute the independent tasks so that we can take advantage of the fact that we have multiple CPUs. After that, we can synchronize the build tasks to make sure that we are consuming the dependencies in the right way, and in the end, we can collect the build artifacts and upload them. Well, there are a lot of issues with this. First, we would have to discover the build graph by ourselves. So we have to perform topological sort by ourselves as well, which is very inconvenient given that computers do this very efficiently. In order to distribute the individual tasks and synchronize them, we need to introduce a lot of custom logic if we want to do this with the state-of-the-art tool in JavaScript. So this is a lot of boilerplate, and there are other issues as well. We don't want to introduce complicated configuration among the individual sub-projects. We don't want to have redundant rebuilds. Imagine if 2 team members are working on the same sub-project, let's say the Google Compute part, the Google Cloud Compute part. If one of them builds the project, we don't want the other team members to have to rebuild it as well. We may want to just reuse the artifacts produced from the build. We may also have cross-language dependencies. This is something that Webpack does not allow right now. We may want to run the end-to-end tests, the integration tests of the front end once the backend APIs change. Unfortunately, we cannot do this with the modern JavaScript tooling right now. And of course, we have team members with different backgrounds. Some of them may have more C++ experience, so they might be fans of, let's say, Make. Others may prefer Gradle or Ant or Maven. Even in the JavaScript world, there is a jungle of different build tools. For example, we have Webpack, we have Build, Grunt, and many others. So we need to agree on one tool which understands how to build the entire infrastructure, all the different projects, without actually knowing anything about specific technology, just being pluggable. What we do instead is let's just ignore all of this and let's try to give Webpack a chance again. So we already saw that, unfortunately, we have a lot of boilerplates for a cold build. But the round-trip time is another very important metric. For example, round-trip time when building a single-page app is when you update a JavaScript file, and right after that, wait until your update reflects in the browser. With Webpack, we saw that this does not scale perfectly. In a project with very small lines, with very small files, we notice that it takes us about 15 seconds between saving the file and reflecting the updates in the browser. In a small project, in a bigger project, this grew up to several minutes. And we can notice this in a lot of our customers as well. For example, in VMware, Capital One, and many other organizations. So Webpack does not scale too well. We already saw that we can eventually make the code build fast by parallelizing to multiple CPUs and reusing artifacts from other builds, but this is still not ideal. We had to introduce a lot of custom logic. So what we do instead is to use completely different tools. And some of them are open source, so we're going to discuss them in details in a little bit. The challenges with Webpack are a lot. So instead of Webpack, we're using something else. We don't like to use, we prefer not to use NPM because of the different security vulnerabilities which are inherited from its design. If we want to stay basically decoupled from the external world, we need to maintain our own custom registry with custom NPM packages. But this means that each package may have different versions. And having multiple versions into the same organization, it's not ideal. Because the individual projects, they cannot take advantage, they will probably not take advantage of the latest security patches that we have introduced in our libraries, because this requires efforts to go and update your source code. What we do instead is to use monorepo. It helps a lot with many different quality characteristics. It helps with reusing infrastructure. It helps with finding and fixing security exploits and propagating them inside of the entire organization. So the entire source code of Google, except a few projects, live in the same repository. You can think of it as the same directory called Google 3. We do not have any security vulnerabilities from NPM this way. If we want to reuse an external NPM package, we're just going to look at its license. If it is appropriate, we're going to open an internal, let's call it a pull request. We're going to try to sync the external dependency internally. A team of experts is going to perform a security evaluation of the package. We are going to see whether we are not going to introduce a security vulnerability in our source code by adding this dependency to our code base. After that, we're going to take a look. After that, we'll be able to reuse the entire infrastructure that we already have internally, right? Because we can have a single continuous integration system for the single repository that we have. It is very easy to reuse knowledge by having a monorepo as well. For example, I can get inspired from Google Search's code base very easily. And we can reuse code just by using very simple relative imports, since everything is basically into the same directory. As I mentioned, we don't have different versions of the individual dependencies, which might seem very counterintuitive at first, because we're used to have semantic versioning, right? We're used to have different versions and different libraries and one project can update it. Like, that's pretty much what we're used to each day to do, to update the dependencies of our projects. Well, the good thing is that once a library changes its interface, introduces breaking change, the author of this library needs to go to all the projects which are using it and fix them. So as part of the Angular team, we have about 1,000 projects which depend on us. And if we break Angular, we need to go and fix all of these 1,000 projects. So we kind of feel the pain of the external users when we release a backwards compatibility. All right, so we don't use NPM. Instead, we use a monorepo. But what do we use instead of Webpack? So over 10 years ago, the infrastructure team in Google developed a tool called Basil. Basil is a universal build tool, which is inspired from functional programming. It is built for caching and parallelism, and it hasn't changed for the past 10 years. It has been inspired from the previous solutions that we used in Google, such as Make, and it grew up from there. How does all this work together? How does Basil work together with our monorepo? If we take a look at the initial graph here, the dependency graph of Google Cloud, and we translate this in terms of directories in our monorepo, we're going to see that we have a single directory, of course, Google 3. Inside of it, there are different projects. We have Angular, Angular Material, we have Google Cloud with its backend and frontend, and we have TypeScript. Notice that how most directories, they have associated build files. The build files, they just create a compilation units. So the files in the directory where the build file resides, they're going to be compiled together. The cool thing is that each individual package can depend on any other package in this monorepo, unless it introduces a cycle dependency, circular dependency. That's it. So packages define compilation units internally, and still this may sound a little bit abstract. You can imagine as just a directory, flat directory with TypeScript files is going to be compiled together, same as a flat directory of Java or C files. They're going to be compiled together, and one package may depend on other packages in this Google 3 directory. Here is an example of a build file. Build file consists of definitions of different targets. For example, here we have ng module and the roll-up targets. The ng module is called src, and it depends on all different TypeScript files in this directory. The roll-up bundle target, it depends on the src main production. So the different targets, they have names and dependencies. They also inputs, excuse me. They also have dependencies. So here we can see that the src target, it depends on to-dos, on Angular core and NGRX store. So these are very important characteristics of the targets. They have names, they have inputs, which are the files that they're going to consume, and also they have dependencies. On top of that, they have outputs. The outputs are very well defined as well. So each target has inputs and outputs, and it does not produce any side effects at all. That's by design. I like to compare Basil and the build that it performs with functional programming. Basically, in the end, we are all inspired from lambda calculus. Later, it evolved to Lisp, I guess, and now it is into more widely used programming languages. So we have functional programming in Basil. We can create mapping between individual concepts. We have pure functions on the side of functional programming, and this roughly translates to Basil targets. We have immutable data structures in functional programming, and this, again, roughly translates to build artifacts. It is amazing that in functional programming, because of these two features, we can take advantage of memoization and running functions in parallel when the dependency graph allows it. In Basil, we can take advantage of these two features as well. Let's take a look how. So here is the high-level execution algorithm as well. We have discovering the dependency graph, topological sort, distributing the independent tasks, synchronizing the build tasks, and collecting the build artifacts. How are we going to discover the build graph? So remember that each individual build file has very well-defined inputs and outputs. They're determined ahead of time. So with Basil, we can just query this directory structure and see what are the individual dependencies among the individual packages. Basil query is going to produce a target graph, which looks something like this. This is, in fact, automatically generated graph on a small project. For the entire Google 3, we will not be able to produce such graph unless we are running it on like hundreds of machines in a distributed network. How do we perform the rest? How do we do the topological sort, distribute the independent tasks, synchronize the build, collect the artifacts? Well, we can just run Basil build. The Basil build is going to produce this build graph, and after that, it is going to run in parallel as many tasks as possible. We're going to take advantage of parallelism. Here is an example. Basically, on 12 cores, we were able to compile Angular because each available core gets already consumed by Basil running a compilation task. For example, compiling TypeScript or even compiling some lower level primitives such as the Go compiler, because it turns out to be a transitive dependency of our development server. So when the cores on our machine are not enough, when the build graph is huge and there are a lot of tasks that can be, a lot of targets that can be run in parallel, we can even run the build in the cloud. That's actually how by default we are building all the applications internally. We can just run Basil builds, and over gRPC, Basil is going to communicate with the build farm and distributes the tasks, distributes the build tasks out there. Of course, this is we need to balance between speed of the build, like distribution, and network latency, because both can be somehow competing goals. So we saw how we can take advantage of parallelism thanks to the functional nature of Basil. But how can we take advantage of memorization? Each individual build artifact, it can be cached. So once a team member in our organization builds a project, they're going to upload all the artifacts, all the build artifacts to a global cache eventually. And anyone else, before building the same project, they're going to first take a look at the build cache and download all the artifacts if available. Basically, each individual build artifact is going to have a key, just produced by a hash function, and it is going to go to static HTTP server. That's it. Basil is going to look in this cache before trying to rebuild given targets. So this way we can share the cache not only across different builds on our local machine, but also across different team members, even between us and CI, the continuous integration system. So we already saw that Basil provides very fast spatial code. How about Roundtrip? Well, Basil takes advantage of incrementality. Basically, the time to rebuild is proportional to the change, not to the size of the project. As you can imagine, once we change a package, Basil can very efficiently localize the change and update only the current package and all the dependent packages if required. So once we update the file, Basil is going to detect the affected packages based on the declared inputs, because each target has well-defined inputs, right? And it is going to compile, analyze their dependencies, and compile the dependencies if required. Let's take a look at a specific example into the context of TypeScript. So we have our to-do application. We have our web application here, which has a to-do target. If we update the to-do target, Basil will have to recompile this package. After that, we're going to check whether we changed the public API of this target, files inside of this package. Excuse me. If we did change it, because of the late, if we did change it, then we will have to recompile the SRC target as well, because it depends on the to-do target. However, if our change did not impact public API, we do not have to rebuild anything else except the current package. This is because of the late linking in JavaScript and in TypeScript. If we change a public API, this means probably some other package may get affected. Otherwise, because of the late linking in the browser, we may not have to rebuild the remaining part of the graph. So how does Basil detect defective packages? First, it calculates the hash of the package by calculating the hash sums of the individual files. Internally, Basil maintains a Merkle tree, which is a very convenient data structure in this case. Let us take a look at it for just a second. So the leaves in this tree, they are the individual files in the file system. Later, we calculate hash of these files, and we calculate the hash of the concatenated cache of the individual leaves. This propagates to the top, and it is a very convenient way for us to check when given target has actually changed, because we can just verify whether the top hash differs from its previous value. From there on, we can just perform traversal of this tree in first order, let's say, and figure out which packages require rebuild. Actually, Basil is open source since 15th of March 2015, and has a lot of other alternatives out there. So, engineers who left the company, they were excited about the system, so they built their own alternatives. Facebook have their own alternative of Basil as well, which has similar approach. If you want to have remote caching in your organization, you can completely do that with Nginx. The setup is trivial. I had to configure this for the Angular team, and I can tell you that, yeah, it was a pretty smooth process. There are open source build farms maintained by Uber and other organizations, and soon the remote build execution is going to be available as part of the cloud as well. What about Gradle? So Gradle is another tool which is very strongly pushed by the Android team, for instance. Gradle is an amazing tool, for sure. It has some differences with Basil. For example, its JavaScript support is less mature. I can comment on this because as part of my responsibility as member of the Angular team is to improve the Basil support, the JavaScript support for Basil. We do not have remote build execution there. And it's, to be honest, it needs to be very precisely configured in order to make sure that it works for small projects as well, and the network latency does not impact it. The configuration languages between Gradle and Basil are different. Gradle uses Groovy, and Basil uses Python dialect, which is called Skylark or Starlark. It is much more restricted in terms of constructs. For example, you don't have recursion there, you don't have loops. It is just pretty much function invocations with named parameters. So this sets further constraints in Basil. It is harder to mess up the build. Both tools have pretty much the same performance characteristics. So if you're using Gradle already and you're happy with it, it definitely does not make sense to switch and to learn a new tool. Well, here are some links that you can take a look at. I'm going to share my slides so that you can actually click these and check the Basil documentation if you're interested. I would strongly recommend you the paper on point 4. It compares Basil with Make, even with Excel, because at the end, on very abstract level, Excel and Basil are not too much different. They are just self-adjusting. They're just systems which maintain self-adjusting computations. So it is very interesting, abstract, and academical paper that is fascinating. So I would strongly recommend this to you. And thank you very much for your attention. I would love to get your questions, probably with a few seconds delay.
Minko, thank you very much for your elaborate presentation. We can now move on with Q&A.
Yeah. Thank you very much for your attention.
Do we have? Maybe I should start. Minko, does latency impacts the speed of the build when using remote build execution?
Maybe I should start. Does latency impacts the speed of the build when using remote build execution?
All right. Yes, the latency can impact the speed of the build when using remote build execution, even remote caching.
Does latency impacts the speed of the build when using remote build execution?
Excuse me, latency currently impacts our Q&A as well. Let me just switch to the live stream on my laptop. Yes. Yes, latency impacts the build execution for sure, because there is a huge overhead from building the actual artifacts, uploading them to the cloud, and after that consuming them. Sometimes when we have to do a cache lookup,
I'm not quite sure whether the connection is quite good. We can't hear
the remote cache. After that, once we verify that the artifacts are there or not, we need to come back, which actually may make our build much slower compared to just running it locally on our restricted set of CPUs.
Unfortunately, we have to cut off the connection and move on with the next speaker just because there's some problems with the connection. I'm sorry about that. You're gonna have chance to just like he said at the beginning, to find him in LinkedIn or Twitter him, so in order to address your questions.
Want to add one thing that, Minko, thank you very much for the presentation, and hope next time you will be in Bulgaria, so we'll be able to ask you many, many questions without any latency delays.